All right, so now we can transition into our keynote this morning. We like to feature an alumni talk every year at the program review. And this year, we're excited to have Dr. Devin Matthews, who is a tenure-track assistant professor in the Department of Chemistry at Southern Methodist University, excuse me, and a faculty fellow of the SMU Center for Research Computing. His research focuses on using and developing accurate theoretical methods to study molecules, reactions, clusters, and extended systems. His specialization is in ab initio methods based on quantum mechanics, combining concepts and techniques from chemistry, physics, mathematics, and computer science. Dr. Matthews obtained his PhD at the University of Texas at Austin in the Department of Chemistry and Biochemistry as a DOE CSGF fellow, and subsequently held a postdoc at the UT Austin Institute for Computational Engineering and Sciences, now the Odin Institute, as an Arnold O. Beckman postdoctoral fellow. He is also a co-recipient of the 2023 James H. Wilkinson Prize for Numerical Software. Join me in welcoming Devin.
Good morning, everyone. It's a great pleasure and an honor to be here again. So, as she said, I was a fellow 2010 to 2014. Okay, so yeah, I know that makes me legitimately an old person, but I'm a young old person. Okay, so keep that in mind. First, I want to congratulate Carlin again, as well as Dipti on the House Scholar Award. You are some of the best graduate students in the world, and I think you should keep that in mind. So today I want to tell you an interesting story that starts in one place and ends up somewhere a little bit different, right? What do ionic liquids have to do with linear algebra? So here's an example of an ionic liquid, okay? And as you might have guessed, there are ions in it, right? And the interesting thing is that it is a liquid, okay? The ions move around in an unstructured way, mostly unstructured, kind of unstructured, okay? So it's not a crystal, right? They're not static ordered, but okay, well, there is actual order, because if you think, well, I've got a positive charge, I've got a negative charge, that's a very strong electrostatic interaction that does induce some order in our liquid. And typical components include things like organic cations here, this would be a B-Mim molecule. And then we have our anion, could be something like bromide, right? Could be a hexafluorophosphate like this. Basically simple, sort of off-the-shelf organic and inorganic compounds, dirt cheap, which is why they're great commercial solvents, right? So this charge gives us great long-range order, okay? What we call charge order. And it gives us sort of these regions of positive and negative charge that create these alternating charge surfaces, okay? And, okay, that's a little bit crystal-like, right? But remember, these are fluxional. They're moving around, okay? And because there are these charged surfaces, right, you can kind of think of them like a huge number of tiny capacitors, okay? That's going to be important. But the fact that we have organic molecules gives us even more ordering here, because, for example, we can have hydrophobic tails here that interact and create things like reverse micelles. Okay? Molecules can come in, they can come out, they can change layers. But we have this sort of statistical picture of order that influences the properties of our liquid. Okay? So they're very complex, dynamic liquids. And so how can we study the properties of these liquids? Now this picture shows you a little bit, right? Now, in terms of the theories of how these are structured and how we can think about these, for example, topologically, this is where we get a little bit interesting, right? Okay. For example, okay, can we think of things as long chains that curl up into these sort of spirals that interact with each other? And what if we have multiple components in there? How do those interact? Okay. So there are a lot of theories out there about how we can classify these and think sort of systematically about their structure. But the experimental evidence is rather difficult to connect to these, okay, because it's difficult to interpret without the aid of computation. And so one particular property of these liquids that I really like is the effect of the electric field induced by the charges, right? And this is where the idea of having tiny little capacitors comes back in, right? Because we have short charge separation, right, we have really relatively intense electric fields, especially compared to large-scale electric fields that we can apply in the laboratory setting, okay? And these can drastically influence the properties, especially, for example, the spectroscopic properties of solute molecules. Even something as plain and uninteresting and nonpolar as carbon dioxide, right, is not only soluble in these liquids, but is heavily influenced by the environmental effects. So spectroscopy then gives us a window into what's going on at the microscopic level of these liquids. And we can measure the spectroscopy, right? But how do we interpret that to then infer the properties of the ionic liquid? And how can we predict the spectra of a new solute without actually putting it in our liquid? Okay? And this is where the computation comes in. And so the method of choice that we're studying is what's called soft X-ray spectroscopy. Okay? So the idea is that we're going to excite electrons, but not the valence electrons. Okay? We're going to excite core electrons, typically of our first row organic compounds. So carbon, soft X-ray spectroscopy, oxygen, nitrogen. But also things like phosphorus and sulfur can also become important, both for their K edges, that's the innermost electrons, as well as the outer core electrons. And so we can ionize these electrons, right? That's X-ray photoelectron spectroscopy. We can excite them. This is X-ray absorption spectroscopy or near-edge X-ray absorption fine structure. Once we have ionized or excited an electron, other electrons can fall down into the core hole that is left over, and that can cause the emission of other X-rays, since we get an X-ray emission spectroscopy. And if this happens in a resonant manner, then we get what's called a resonant inelastic X-ray scattering process, or RIX. Okay? So there's a lot of different experimental techniques that we can use to study these. The nice thing is that theoretically, they're all really the same process, right? They're interactions of the ground state, core excited or ionized states, and regular valence excited or ionized states. Okay? So if we can calculate those states and the properties between them, then we can simulate all these different types of spectroscopy and connect that to the structure as input to our quantum chemistry calculation. Okay, so what does this kind of look like? Okay, so we'll take a simple molecule here. We'll take a uracil. And the first interesting thing to note is that we don't just get one X-ray spectrum of this molecule, right? We get several, because the X-ray spectroscopy that we do is element-specific. Okay? The core electrons of different elements sit at rather different energies, okay? Around 400, around 280, around 529. Okay? That immediately tells us, oh, this is nitrogen, this is carbon, and this is oxygen. Okay? And then the individual peaks in these spectra tell us something about not only the individual atoms in our molecule, but how they interact with the excited states of our molecule. And so it's not quite like, say, NMR, where you say, oh, well, this is this nitrogen, this is this nitrogen. It's actually an overlay of something more like a UV-Vis spectrum, but for each atom and with their own individualized intensities and positions of the absorption lines. And then you overlay those together, and you get this X-ray absorption spectrum. Okay? So sometimes we get lucky. Okay? So here we see there's two very clear peaks, which correspond very clearly to these terminal oxygens here. Okay? And these are pi to pi star excitations, exactly what you'd expect. But if we look here or here, we can see there's actually a very large number of individual excitations that make up many of these peaks. And so interpreting them is not particularly straightforward. Okay? The other really interesting thing about X-ray spectroscopy is that we can use it as a probe of dynamics of processes. Okay? So this would be ultra-fast X-ray spectroscopy. And so we can see changes in the spectrum during a process that come from movement of population of molecules from the ground state to excited states, valence excited states typically. And what we see is actually absorption from the valence excited state to one of these core excited states. And this brings in new features to our spectrum. Really, what we're looking at here is this little bump. Right? That little bump is the smoking gun that tells us exactly what pathway we take to internally convert the energy of an initial UV excitation in our molecule. Right? And there's a lot of argument here whether is this a pure pi star, is there a pi sigma star involved, or is there n pi star? Right? And this says, yeah, this is definitely a pi star, n pi star internal conversion. Okay? And that was information that's very difficult to get with other techniques. Okay, so at SMU, what we're doing is we're trying to create a computational methodology to study and predict these kind of spectra. Okay? And there's a lot of different aspects of this that we really have to get right. And we have to get every one of these right. We can't just get this one a little bit, this one a little bit, oh, it kind of works out in the end, right? Because that's a very fragile and not predictive way of doing quantum chemistry. We have to get each one within the error bars of what we're trying to predict, the experimental uncertainties. Okay? So we need to deal primarily with something called orbital relaxation. Okay? And what happens here is that as we excite or ionize a core electron, that electron is no longer shielding the other electrons from part of the nuclear charge. Okay? And in essence, what happens is that our oxygen atom, if you remove a core electron, looks a heck of a lot more like fluorine. Okay? And actually starts to behave chemically somewhat similar to fluorine. Okay? And so this induces a radical change in the other electrons' behavior. And in terms of quantum mechanics, the shape of the molecular orbitals that they inhabit. Okay? So that needs to be taken account of in our calculations. We need electron correlation, that is the instantaneous interactions between the electrons. Because even though if we get this relaxation right, okay, how does that affect then the ensuing excitation process? These are coupled processes here. We need the correlation between electrons that comes through instantaneous interactions. We need to pick a good basis set. Okay, this is essentially the spatial discretization of the wave function that we're using. Okay? And we have sort of predefined sets. We say, okay, well, I have these functions, and I put them on this atom, and these functions, I put them on that atom, right? But the general rule is the more functions, the better you do, okay? But the more functions, the more expensive the calculation is, right? So what's the balance between those that satisfies our chosen error bounds? And then here, for the science that we want to do, how do we then couple all of this to the environmental effects, right? Starting with something like an external electric field, and then working up to a full electrostatic or quantum embedding of the environment, including dynamics. So in terms of orbital relaxation and electron correlation, we decided to treat these together, okay? We're using what are called equation of motion coupled cluster techniques. Okay? And so these have been shown to be very accurate for valence excitations. A particular method called EOM-CCSD. Okay? Now here the SD is the important part. Okay? It means we have, in our wave function, we explicitly represent single and double excitations of electrons. Okay? Well, the single excitations, that's just the UV excitation process, right? The double part means that we have actually two electrons that are doing something. That's correlation. Okay? They're doing something, but they're doing something together in a way that is interdependent. Okay? That's what gives us electron correlation. And in order to treat the relaxation, well, one option is to say, well, if we put a third electron in there, that describes a little bit of our relaxation process. And we want to, we can put a fourth electron in there. Okay? But now our costs have skyrocketed. Okay? So the CCSD star is really the simplest triple excitation we can put in that treats that orbital relaxation, but it's still rather expensive. But we can see, the errors do indeed go down quite a bit. And these are two other methods that we've come up with that either don't have triple excitations, that's this transition potential coupled cluster, right? But yet it explicitly treats the orbital relaxation and the electron correlation. Or this method here, where we include the triple excitations in an extremely targeted manner such that it doesn't increase the cost of the calculation. Okay? In particular, it doesn't increase the scaling of the calculation. We'll come back to that. So we have some good methods, we think, that we can apply to these techniques. Okay? Well, what about the other categories? Okay? Well, if we look at basis sets, okay, this is a very ongoing area, but the idea is, well, we have standard basis sets that work well for the ground state. They sort of work for excited states, but they really don't work at all for core excited states. Okay? So let's make some boutique basis sets, specifically designed basis sets just for this property, and maybe we can get away from our usual Pareto, basis set number versus cost versus accuracy curve, right? That was actually this orange curve here. That's our standard basis sets. So yeah, we can approach the right answer, but we get there really slowly. Okay? So we've designed one line of boutique basis sets so far where we actually take just the core part, the S and P orbitals, which are the ones that react most strongly to relaxation, taking those from a large basis set, and mix that with other functions for other types of orbitals, higher angular momentum orbitals that are not involved in relaxation, and for the other atoms in the system, right? Because the core electrons are tightly localized. They don't affect other atoms in our system. We can use a different basis set. So when we do that, we approach the correct answer much, much, much more quickly. Okay? And that's going to drastically reduce the cost of our calculations while hitting our target error bounds. So, okay, now what about an electric field, right? We're very interested in those. So we've done some initial studies so far in small gas phase molecules to study, okay, well, how does an electric field impact the structure of these X-ray absorption spectra? Okay, so we found some interesting things. First of all, the strength of the electric field is extremely important. Okay, so up here is something like it's a typical field of an ionic liquid. Also, electric fields that you can find in things like biomolecules, proteins, okay, inside the binding pocket, for example. And we can apply those in different directions here. And we can see there's a huge modulation of the position and the strength of these absorption peaks. Okay? Some of them are nice and simple. Okay? Some of the pi star excitations, for example, it's a straight line. Okay? Linear Stark effect. Great. Well, okay, some of them are bent. Okay? Here we've got a little bit of a bend. That's a quadratic Stark effect. And then some of them kind of do whatever the heck they want. Okay? And they wiggle all over the place, and they grow, and they shrink, and they mix together, and they do all sorts of stuff. Okay? But because we're doing the calculation, we can assign these very easily. We can calculate things called natural transition orbitals, and we can make little pictures to see exactly where the electron density is accumulating or moving from in these molecules, and how that's affecting the electronic structure and the spectroscopy here. Okay? So these can give us clues to how to interpret experimental spectra. We've also looked at the effect of oriented electric fields. Okay? What if I could design my system such that I could apply an electric field from a very specific angle? Okay? How does that differ from if I let the molecule rotate to its natural orientation? Right? What if a molecule could have multiple natural orientations, right? As we have here. We have two minima on this rotational potential energy surface, right? And how can we use that to control the properties of molecules, right? So very interesting, but early research right now. Okay, so let's say, for the sake of argument, that we've solved all these problems, right? We've got the right electron correlation, we've got the right orbital relaxation, we've got great basis sets, and now we can study the effect of the environment on the molecules, okay? So let's go do it, right? Okay. Well, there's a problem. If any of you have heard of equation of motion coupled cluster, you know what this problem is. Okay? If you haven't, think of DFT, right? DFT is great, it's accurate, right? But it's not the cheapest, right? Okay? You know, it's kind of the heavy hammer you put, right? We're taking out the sledgehammer here, okay? We're way beyond DFT. We're going to get the right answer, but it's going to cost us, okay? And what it's going to cost us is scaling, okay? And the good scaling we get by not including triple excitations means that every time we double the size of the system, we increase the cost of the calculation by a factor of 2 to the 6th, okay? And graphically what that means, and note the very non-scientific y-axis here, is this, okay? So we're doing great, we're doing great, we're doing great. Well, okay, so much for that, right? So we need to reduce the scaling of these calculations. Otherwise, we can never study anything other than very small molecules in very simple environments. Well, maybe we can learn some things from that, but it's not going to be, you're not going to change the world, right? You know, it's a very limited application. So to increase the scope of applicability, we have to bring the cost down, right? Not by a constant factor of 10, by factors of 1,000, 1,000,000, right? That we only get from this scaling. What is the exponent, right, what we get when we increase our system size? So, well, we can turn to Walter Kohn here. Right? And Walter Kohn, you know, one of the originators of the density functional theory method, he noted in a very important article that electrons really only interact in a localized manner. Okay? They have a nearsightedness to their quantum effects. Okay? Of course, there are long-range interactions, right? But these are really classical and electrostatic in nature. Okay? Everything else is sort of localized, right? Basically, this means there's a structure to the quantum information of a system, right, that should be exploitable in some way, okay, and which should not be intrinsically high scaling for large enough systems that cross this nearsightedness horizon, okay? Now, one way we can do this is by actually localizing our description of our molecules. It's called orbital localization, okay? So once we do that, then we can sort of decompose our calculation into tiny little bits, right? We can do tiny little calculations, we can put them back together. Okay? That's one technique. For example, a technique called DLPNO CCSD parentheses T, okay? Very helpful, okay? But it doesn't naturally extend to the kinds of things we want to do, like excited state studies and transition moments. What's a different way we could apply this, right? We could think instead of local structure, we could look for global structure, right? But global low-rank structure, okay? So we can describe interactions sort of from a overall picture that doesn't have the intrinsic high scaling that we would normally get, okay? So one way that we can do that, right? Well, we're going to look at it, okay, so we're going to look at tensors, right? This is an interaction of, a representation of the interaction between two electrons, okay? And if you like, you can think of this kind of like scattering. So we have two electrons coming in. They're initially in a state, okay, in our case, a molecular orbital. We could call those R and S, right? And then they're going to interact, that's the dotted line here, and then they're going to end up in a different state, okay, molecular orbitals P and Q, okay? The problem here is that we have to tabulate the strength of this interaction, the amplitude, for every combination of P, Q, R, and S, all right? That's n to the fourth, okay? And then we think, okay, well, this is just the interaction. Then we need the wave function, okay? In order to get electron correlation in our wave function, again, we need 4 indices, n to the fourth. We take an n to the fourth thing and n to the fourth thing, we put them together. They overlap a little bit, but that's where n to the sixth comes from. And that's it, right? If you have an electron interaction like this, you have a wave function that includes electron correlation, n to the sixth, right? Not much you can do. But we can take this exact form, right? And we can do a decomposition, right? Come up with an approximation, and it inherently is an approximation that has a simpler form, okay? So here we've taken one tensor, we've written this as the contraction, okay, multiplication and summation of two tensors, each one having 3 dimensions, okay, great. Okay. And you can actually kind of think of this kind of like an SVD, right? A singular value decomposition, okay? Which is low rank. J is much smaller than the product of P and R here. Okay? Problem is, this particular technique reduces the size of the things we need to worry about from n to the fourth to n cubed, but it does not reduce the computational scaling. In fact, once you do calculations, you actually end up having to multiply these back together, get this, and then go on your way. Okay? So we need a different type of factorization. Okay? Well, what about this one? All right, so this is something called the canonical polyadic decomposition. Okay? And the idea here is that every incoming edge, right, every representation of a single electron, we can compress, right, or transform into some auxiliary space using a factor matrix. Okay? So we have factor matrix U, V, W, X. And then the interaction here is represented actually in a linear space, lambda. Okay? And from a graph theory perspective, right, we think of this as a graph. This lambda would be a hyperedge, okay, connects to multiple nodes. And this has computational ramifications. Right? So there are some problems here. There is actually some really nice, important physical symmetries here that we end up losing. And actually, obtaining this factorization requires a complex nonlinear optimization process. Okay? So what else can we do? Well, we'll go back one step, and then forward, we'll say, okay, well, we'll take these little triangular guys, and we'll do a canonical polyadic decomposition of one of the triangles. Okay, so we get 1, 2, 3 factor matrices. Now, this factor matrix, we can just multiply in here. We can absorb it in that other factor. Okay? So we get this kind of weird situation here. So we get 2 and 3-dimensional tensors, this being just a matrix, and a hyperedge here. Okay? And it turns out this is enough to start reducing our scaling, okay? But it's still difficult to obtain, right? So I think, okay, we'll go another step further. We'll factorize both sides, all right. And now the factor matrices in the middle can't be absorbed into anything else, so we multiply them together and get this core matrix V. Okay? Now this is a picture I like because it has a physical interpretation. Right? We can think of this as taking, and here, this is really electron 1 engaging a scattering process with electron 2. Okay? And this electron 1, we're compressing the initial and final states into the linear scaling auxiliary space R. Okay? And we're compressing this into a similar linear scaling auxiliary space S. And then those interact. So this is actually our physical interaction in this auxiliary space. Okay? Interesting. And this compression step then reduces our scaling. Then we can go further and we can say, okay, well, what should this auxiliary space be, right? Since we're having a physical picture, let's pick what that auxiliary space is. Let's make a grid, okay? A lot of you have dealt with grids, right? Grids and meshes, okay? So we know how to deal with those. In particular for a molecule, we know how to deal with those because we need grids for density functional theory. Okay? We just take those directly. And so that gives us a discretization onto this auxiliary space. Then all we need to find is V. In fact, that's a linear least squares process that we can do very efficiently. Okay? So what does this mean? Well, okay. Now that we've chosen this auxiliary space, actually finding this matrix X is super easy. We just take our molecular orbitals, we evaluated a bunch of points, there's our matrix X. Okay, that was easy. But what does this mean? Well, if we plug this into our formula here, this guy is an integral, right? Kind of an interaction integral. This looks like a double quadrature. Right? We just take our integrals, we make them sums, okay? Sums over quadrature points, that's our x's. Quadrature weights, those go here somewhere in the middle. Okay? Now, you get singular terms here, right? You can't evaluate this directly except in the solid phase where you can do it in momentum space. But the linear least squares takes care of that. We sort of take this out and say, I don't know what that is, I'll fit it. Okay? But that's our interpretation. We're really just doing a double quadrature, right? We know how to make good quadratures. Okay? So we can do that, and this should be accurate. Okay? And it's very similar to the same kind of thing we do in DFT. Okay, so that was the interaction. I mentioned the wave function, right? What about the wave function? Well, we could think of doing the same thing, right? We have two orbitals here that represent electron 1, and that interacts through a correlation effect with electron 2, and we can compress those into this space R and this S. Heck, we could even use the same grid and the same X matrices as in our linear least squares process, right? And we can do a linear least squares solve for what this guy is, okay? And find a good representation of our wave function. We can even do that iteratively, right? By solving the Schrodinger equation, okay? But instead of updating this entire vector, wave vector, okay, we can update just this little part here, okay? So we've done a compression. And that also reduces the scaling. Well, now we have a problem. So we're going to look at the very simplest post-DFT method we can. This is MP2, second order multiplicity theory. It actually turns out we get the same qualitative, even quantitative picture if we go to more complicated methods like CCSD. Okay? But we can actually take that energy in particular and decompose it into two parts. Okay? We call the Coulomb energy, we call the exchange energy. Okay? And this is nice because the Coulomb energy really depends on the factorization of the integrals, okay? Not the amplitudes. And actually, you can show that mathematically. Whereas the exchange part, no matter what you do, requires some sort of factorization of the amplitudes, okay? And we can look at the error in these two components, okay? And here we've normalized them. And we can look how that changes as we increase the number of grid points, okay? Which should increase the accuracy and eventually converge to the right answer. Okay? So the Coulomb energy converges quite quickly, right? Even exponentially here, right? But the exchange energy converges much, much, much more slowly. And we have this gap here, right? And that's due to attempting to compress the wave function using the same technique as the integrals. It's simply not as effective, okay? And that's really when we get down to it because we don't have the same physical picture of what this compression means for the amplitudes. Right? The amplitudes are inherently not the same kind of thing as our electron interaction. Okay? So what we've been looking at is, well, really what we did is we picked a basis, right? Basis for our compression. works great for the integrals. Now we know that there is some basis that works for the amplitudes because we can resort to a nonlinear factorization where we determine all of the factors at the same time. And sure enough, it's perfectly compressible. Same errors as for the amplitudes for the same size basis. But what is that basis? It's hard to say, right? All we know is in the end what the basis is evaluated in some space. We don't know the underlying functionals that define that basis. Okay? So what we've done is we've pursued a strategy where we look at both the geometric properties here by overlapping an orthogonal subspace onto a singular value decomposition of the thing that we're looking at, our target, okay, and normalizing that. And that gives us basically a singular value weighted geometric overlap, an importance score that we call F. Okay, something between 0 and 1 that tells us how important is a particular basis function to our factorization. Okay. We can also look at the energy, and we say, okay, well, if we add this basis function, how much does our energy change, right? How much closer do we get to the correct energy? Right? And we can rank basis functions that way. And then we can take these rankings, either the energies or these importance values, and then we can correlate that with something about our basis functions, right? So we've been looking at basis functions which are derived from pairs of points, okay? And pairs of points is kind of a logical extension to say, well, if we have two electrons interacting through electron correlation, right, we need to know what's happening at two distinct places in space. Okay? Kind of makes sense. And we're just going to add that information together, right? So we still get separability because we're just adding things together, but we're adding information from two places at once. Okay? So we get an interference effect from that. And then we can look at, for example, what is the geometric relationship between these points, right? We can think of angles to atoms. We can think of distances, okay? Now, the distance in particular is interesting, right? And we go back to Walter Kohn, his nearsightedness. He mentions the Compton wavelength of an electron, okay? We can compute that for an organic electron, right? Valence electron. Turns out, Compton wavelength is right there, okay? So he was right on the money. Turns out that electron correlation does actually decay on the order of the Compton wavelength of the electron. We have actually direct computational evidence of that. I think this is very exciting here. So then the idea is that we can use that to design extensions to our basis set, right? They can then capture directly these correlation effects and close that gap between the exchange and the correlation energies. Okay? All right, well, I promised you reduced scaling, right? All right, here it is. Here's a scaling plot. Okay? So what we've done is we take system size, we've taken running time, put it on a log-log axis. So the slope of these curves gives us the power of our scaling law. Okay? So the orange curve is our standard calculation. And if I fit this, I do indeed get something very close to 6, okay, and to the 6th power. And I can do these tensor hypercontraction methods. Okay? Now, I could do it very, very, very naively, okay? Not great. I could do a better job. I can do an even better job, right? And then we want to see, where does this cross over, right? How big do we have to go before the scaling, right, which favors the THC, overcomes constant factor, which favors our traditional method, right? So we do have a more complex method. Now, this is not great, right? If we go down here on this axis, we get around 32. Unfortunately, that's not 32 electrons. That's 32 carbons in an alkane chain. Okay? So this is a couple hundred electrons. Right? That's pretty large. And we have to go even larger than that to see significant savings. That's not great. Okay? Now, more recently, we've been able to tune things such that we can boost that further. Right? There's a lot of curves here because we're doing a lot of different sizes of grids. Okay? But if we look here, this is our scaling plot. And they cross somewhere around 12, okay? All right, we've gone from 32 to 12, okay? That's less than 100 electrons, okay? It's about 80 electrons if you include the core electrons, right? So we can reduce the scaling while getting a crossover somewhere in the right range, okay? So the scaling part is actually fixed. Okay, we've got the right scaling. Now the battle comes actually back to constant factors, right? We want to move this crossover even more so that we can easily access this area where we get these huge computational savings, right? So we've got to turn to our high-performance computing implementation of these methods, right? And we've got to do those flops as fast as possible. Okay. So let's see what a little bit of this implementation looks like. Okay. So here's a graphical representation of one of the terms that we have. Okay. And it's the same kind of little pieces that we had. Okay. Here's a wave function piece, a wave function piece, an interaction piece. Okay. That's a expectation value. Okay. Quantum mechanically. We're going to decompose this. Okay. And then we can come up with a factorization, that is an order of performing these terms, right? That gets our correct scaling. Oh boy, it's this guy at the bottom, okay? And these grouped areas here represent computational primitives. These are the computational things we actually need to do. Like, this is a function I need to call that has inputs and gives me an output, and I want that thing to be fast, okay? Some of these things we know how to deal with. This guy right here. That's a matrix multiplication. Okay, what do? We call BLAS, right? Basic linear algebra subroutines, MKL or something. Okay, great. That one's fast. Uh-oh, what about this one? Okay, what do we do here? What about this one? What if we include this factor additionally, right? And what we do if we look at these things, right? We could start modifying this a little bit. We could say, okay, well, we'll sum over this one first, and then we'll sum over these ones, break it down further. We get things that eventually look like BLAS, okay? Look like linear algebra operations, but they've got stuff tacked onto them, okay? Turns out that stuff tacked on, that can easily take greater than 50% of the computational time, right? There's a factor of 2. It's even as high as a factor of 10 on the table here if we can merge those into our computational kernels and maintain high speed. Okay, so how are we going to do that? Okay, now there's a lot of potential computational kernels that we could think of. Okay, these are some of the ones that I've come across in my work. And we want a framework that is all of them, right? We don't want to write this function and then that function and that function. That'll take forever. We want to do all of them. Okay, so we'll look at how BLAS works. Well, we'll look at how BLIS works. Okay, so BLIS is a particular instantiation of BLAS, but one that is a very clear framework. Okay, so along with Field Van Zee, this is what was awarded the Wilkinson Prize that was mentioned earlier. So, okay, how do we make BLAS fast? Okay, that's it. That's right. We'll bask in its glory. Okay, that's it. Okay. All right, now, what does that mean? Okay, so we can think of taking a matrix multiplication, and we'll make it recursive. We'll do a big matrix multiplication. That's going to be a bunch of small matrix multiplications, right? We can do that 3 ways. Okay? Now, if I had more time, I'd tell you how to do this algorithmically, along with a proof of their correctness, but that's a story for another time. But we got to think about it. We got 3 dimensions. We could just do a loop over one of those 3 dimensions. Okay? Important thing, in each of these algorithms, one of the matrices does not change. It's stationary. Okay? So in terms of optimizing data movement, we can think, we'll keep that one in some level of cache. The other 2 will stream. Okay? And this is a recursive algorithm. We can recurse and recurse and recurse new turtles all the way down, right? So we're going to look at the cache hierarchy of our processor and use that to design an algorithm. Okay? We're going to start with the registers. We'll say, okay, well, what matrix are we going to keep in registers? We'll keep C in registers, right? We'll stream the other 2. And then what? Okay. All right, then we'll put A in register, let the L1 cache. Okay, and keep streaming. Oh, sorry, B in the L1 cache here, right? Then we'll put A in the L2 cache. Okay, we'll put a bigger part of B in the L3 cache. Okay, and then we get up to memory, and then we have our complete implementation. Okay, so by nesting together these recursive algorithms, we can design exactly a complete algorithm that utilizes each level of cache, and in fact, we can prove how close to optimal usage we are based on the shape of these matrices. Okay? So that's the basic idea, and that's where that picture comes from there. Okay? So we encode that using something we call a control tree. Okay? It says at each step, what is our next sub-algorithm going to be? Okay? Which one do we partition next? We have to do this thing called packing. And that's so that we can ensure linear access at the low level so that we don't have page faults and other things like that. Okay? But, okay, that's GEM. Let's just make multiplication. What else can we do? Right? Why not do other stuff there? Control tree can do anything. Okay? We could do computation while packing, right? We could scale each row or column. That's something we need for one of the operations I showed you earlier. We could load data from a different format. Instead of having a matrix, what if we had a tensor, right? What if we had a structured matrix, right? What if we're computing our matrix on the fly, okay? The data could come from anywhere. It doesn't have to come from a standard matrix. And once I've computed this, I can do stuff to it, right? I can post-process it, okay? And I can put this all into my control tree, and I know I'm going to get the same performance because I'm still optimizing my data usage, and I'm still using high-performance microkernels, things like we were writing assembly, but then just modify, okay? So yes, I can do all of those things, okay? And so what we've done is we've made Bliss now into a framework, okay? So it does BLAS, right? That's sort of the obvious plug-in for it. But it can do so much more. Okay? So some of the examples that people have used this for in the literature are things like tensor contractions, one that I did, k-nearest neighbors needed for machine learning, something called linkage disequilibrium from computational biology, of all places, right? Image convolution for machine learning. So there's all sorts of things we can do with this framework, right? Including quantum chemistry. All right, so with that, I'd like to thank my group for all their hard work and our funding sources. This is what happens if you don't show up for photo day here. I'd like to mention all of the people who contributed to Bliss over the years and all the funding sources for Bliss over the many years that it's been growing now. And I'd like to just reflect a little bit. When I was a fellow, I got the great opportunity to interact with other fellows, for example, Jeff Hammond and Edgar Solomonic and Sam Blau. And working on Bliss and these other projects has really reinforced the lessons that I learned as a fellow. It's that collaboration is very important, right? Use your time here at the program review and at your practicums, because people that you meet here can be your collaborators for a long time, can do really great science. And that software, especially open software, right, can really have an impact on the community. And so the software that you write is very important. So, and of course, being in this room, I also just have to add, yes, I'm hiring postdocs. So, all right, now I'll take some questions.